Hi everyone. We have been discussing about the design issues of data link layer. We covered framing techniques. We also covered the error control mechanisms, which included error detection and error correction as well. And it's time now to discuss about the third important characteristic or the property of data link layer, which is your flow control. So simply put, flow control is something where the sender can only send the data according to the capability of the receiver. So only when the receiver says when and how much, only then the sender can send that many number of frames. So to put this into practice, we discuss something called as sliding window protocols. So earlier we started our discussion regarding the simplex protocol and then the simplex protocol for noiseless channel and also the stop and wait protocol for noisy channel. So all these protocols, the earlier ones, are having the same assumption that the data is going to be transmitted in only one direction, that is from sender to receiver. But for practical usage, talking in a way where there is only one part or one way communication is not going to happen. So for practical applications, the data transmission has to be bidirectional. So interleaving the data and control frames on the same link is a better option over maintaining two separate physical links. So if I have to have bidirectional communication, what generally happens is if I have a sender and receiver, one link will be dedicated for onward communication and another link will be dedicated for reverse communication. So for A to B is one link and B to A is another link. So rather than maintaining two links, which might be an expensive option, what we can do is we can have the same link where the data and control frames are interleaved. So we can send one after the another. But there is also another better option which will enable us to send the acknowledgement for the data that we sent on its own rather than having to create a new frame is called as piggybacking. So let me explain to you what this concept is. So imagine that A is the sender and B is your receiver. Now A has sent a frame to B. A has sent a large frame F to B. Now B, after receiving this frame and after checking, verifying whether the frame has been received without any errors or not, then decides to send the acknowledgement back. Acknowledgement is nothing but it's a very small packet which just tells you whether the frame has been received by the destination or not. So which conveys to the sender that this frame has been received and has been received without any errors. So to send this acknowledgement, once again, it has to be kept in the header, a frame which includes the header, which includes the trailer, all those things. So imagine a situation where if we can add this acknowledgement to the next outgoing data frame from B. So if B is going to reply to this frame with its own data, if I am able to add this acknowledgement to this new frame or the next outgoing frame, I can save all this overhead. That means I can utilize the bandwidth efficiently. So rather than sending the acknowledgement separately, what I will do is I will add this acknowledgement to the next outgoing frame and then transmit this to the receiver or to my other peer. So this technique of temporarily delaying the outgoing acknowledgements so that they can be hooked onto the next outgoing data frame is called as piggybacking. So piggybacking is generally used in all the networks, where as I told you, so when the frame from A is received at B, B after verifying that frame has to send an acknowledgement to A confirming the receipt of this frame. So instead of sending this acknowledgement on its own, what I'm going to do is I'm going to make B add this attachment to the next frame that B is going to transmit to A, so that A need not be sent on its own or the acknowledgement need not be sent on its own and it gets a free ride with the next outgoing frame. So instead of just sending one acknowledgement and one data frame, I'm now sending this entire thing as one frame. It is saving my bandwidth. The primary advantage of the piggybacking is better use of channel bandwidth, but with additional system complexity. You might ask me, sir, where is the complexity here? So what if B doesn't have a frame? And how much time can B wait to see if there is any frame or not? As we discussed earlier, A after transmitting this frame starts a timer, isn't it? A timer is started for every frame that is transmitted. And before the timer expires, A is expecting an acknowledgement back from B. And if this acknowledgement is not received at A before this timer expires, A will retransmit this frame again. So A retransmits the frame if it does not receive the acknowledgement. B, on the other hand, wants to wait till the next frame arrives so that it can add this acknowledgement and then send out to A. So there is a slightly sensitive situation here where how much time that B has to wait for the next outgoing frame. What if there is no frame at all? In those cases, this system complexity comes into play. Usually what we do is we put another timer at the receiver just for the sending of this acknowledgement. So how much time that B can delay this acknowledgement so that this acknowledgement goes to A before the timer expires. If the timer expires and A retransmits again, so this whole idea of saving the bandwidth, doing piggybacking is utterly waste, because A is retransmitting the frame which has been received perfectly with the destination. So this is regarding piggybacking. And let us discuss something called as sliding window protocols, which are all bidirectional in nature. So the following three protocols belong to a class of bidirectional protocols called the sliding window protocols. The first in this particular category is the 1-bit sliding window protocol, and the second one is go back N sliding window protocol. Usually it is represented as GBN. And the third one is the selective repeat sliding window protocol, which is usually represented using SR protocol. So if you see these things also, it's the same thing. Now, for these sliding window protocols to work, the first and foremost requirement is that each and every outbound frame or any frame that is outbound must have a sequence number attached to it. If unless until there is a sequence number to the frame, it cannot, these sliding window protocols cannot work. These frames, if you ask me, sir, what is the sequence number range from? What is the maximum range that it can have? So there is no such thing. What we do is you select how many bits for the sequence number. Now let me as an example, if I say that my sequence number consists of 3 bits. So the range of the sequence numbers that I can have is 0 to 7. So 0, 1, 2, 3, 4, 5, 6, 7, because it's 2 cube. So if you ask me how did I get this 7, it is nothing but 2 cube minus 1. Now you can see this. The maximum is usually 2 power n minus 1, so that the sequence number fits exactly in an n-bit field. So if I say that the maximum sequence number that I'm going to take is 0 to 15 or 15, that implies that a 4-bit sequence number is used. You have to understand in such a way, okay? So the maximum is usually 2 power n minus 1, so that these are the n stands for the number of bits in your sequence number. As discussed earlier, the stop and wait sliding window protocol uses n is equal to 1, restricting the sequence numbers to 0 and 1. If you ask me, sir, why just 0 and 1? What is the issue there? Because in stop and wait sliding window protocol, the sender sends only one frame and has to wait for the acknowledgement to be back. Unless until the sender receives the acknowledgement from the receiver, it cannot proceed further. So in that case, so you're always going to have only one frame outstanding and one acknowledgement. So first I will send with the sequence number as 0, and if I get the acknowledgement back, I will increment it to 1, and if I get the acknowledgement back, I will increment it to 0, and so on and henceforth. That is the reason in stop and wait protocols, usually even the sequence number, 1-bit sequence number also works. Okay. Now, once again, if you are wondering about why there are 3 different protocols, all the 3 protocols actually differ among themselves in terms of efficiency, complexity, and buffer requirements. Now, if you want to understand where the complexity is and what are these buffer requirements, you have to understand 2 terms called as sender's window and receiver's window. You have to understand about these 2 terms. These are the terms which actually are very important when you're talking about these 3 protocols. Let me explain what these 2 terms are. So these 3 protocols are going to be going to have some kind of difference in terms of efficiency, how good they are, the complexity, how complex they are to implement, and finally, what will be the buffer requirements at both the sender and receiver. Okay. Now, let me show you. As I told you, For this to be understood clearly, the most important point is how do you understand what a sending window is, or how does the sender maintains this window, and similarly, what do you mean by a receiving window, what it has to do with the receiver. So to define what these things are, a sender's window or a sender maintains a set of sequence numbers of the frames it is permitted to send. These frames fall within the sending window. So as the name itself suggests, the sending window is at the sender side, and a receiver maintains a set of sequence numbers of frames it is permitted to accept. These frames fall within the receiving window. So it is at the receiver. Okay. So to understand in a way what these two things are, as I told you to discuss about the sequence numbers, isn't it? Now let me take another small example to tell you. Now if I have A as sender and B as the receiver. Now if I tell you that A has the capability of sending 3 frames at a time without waiting for an acknowledgement, the sender's window size will be 3. And if I say that B's capability is to accept 4 frames at any given point of time, the receiver's window size is 4. So here the sender's window size is going to tell me that how many number of frames that the sender A can send without waiting for an acknowledgement. So if I put the sequence numbers as 0, 1, and 2, it can send all these 3 out and then wait for the acknowledgement to come back. Okay. Now we'll take another example. I'll tell you more in detail. The sequence numbers within the sender's window represent frames that have been sent or can be sent, but are as not yet acknowledged, which means that the sender has sent these frames, but the receiver did not send an acknowledgement back. If the sender receives the acknowledgement for the transmitted frames, it simply slides the window to the next frames. As I told you, just give me a couple of minutes so you will be able to understand this better. So the sequence number within the sender's window represents the frames that have been sent or can be sent either way, but are as yet not acknowledged. If they are acknowledged, they will never be a part of the sender's window. As frames may be lost or damaged during transit, anything can happen. There might be errors, or it might encounter something, or it might be completely lost. They must be kept in memory for possible retransmission. So these three, the sender's window tells you how many buffers the sender has to maintain. So unless until the sequence number or the acknowledgement for these 3 frames comes back, these frames of sequence number 0, 1, and 2 has to be kept in the memory. Because if any of these is lost, the sender has to retransmit it again. But once the acknowledgement is received, it can remove them and it can place with the new frames. So if the maximum window size is n, the sender needs n buffers to hold the unacknowledged frames. So as I told you here, the sender's window is 3. Imagine if it is 7. If it is 7, I need 7 buffers to place the frames. 1, 2, 3, 4, 5, 6, and 7. So here the sender's window pertains to the buffer size at the sender. What do you mean by buffer size? The buffer size relates to how many number of frames that the sender can hold in the memory to send or waiting to be acknowledged. That is called as your sender's window. The same happens with the receiver's window also, but it is slightly different because the receiver's window contains the sequence numbers of the frames that the receiver is expecting from the sender. So the receiving data link layers window corresponds to the frames it may accept. So this is the diagram which I brought from the Faruzam. You can see this blue colored one is your data link layer at the sender and the same one at the receiver. So when the sender's network layer sends the packet to imagine that this is a packet, sends a packet to the data link layer. What does it do? It will put a sequence number to this and then the header and everything. So this packet becomes a frame and then this frame is transmitted. It becomes a frame and this frame is transmitted to the receiver. At the receiver side, at the receiver side, once this frame has been received, it will check, it will verify whether this has been received without any errors or not, whether this is the same frame it is expecting or not, and then it will send an acknowledgement back. This is your acknowledgement. Only once the acknowledgement is received by your sender, it can proceed on to the further. So a sender's window always contains the sequence number of the frames that the sender is currently waiting for. Or, of course, the waiting for can be two things: sent but not acknowledged, yet to be sent. So it is waiting for them to be transmitted, or it is waiting for them to be acknowledged. At the same time, on the receiver side, the size of the receiver's window is going to tell you, or it contains the sequence number of the frame which the receiver is expecting next. Okay. Now let me show you a quick and a small example to get this idea. In my example, this is my sender. Let us say this is A and this is my receiver B. On sender, let me say that the sender's window size is equal to 7. So what this means is the sender has got 7 buffers, and at any given point of time, it can have 7 outstanding frames. Outstanding frames. If you ask me what do you mean by outstanding frame, this means it is either to be sent out or either to be acknowledged. That is what we call as an outstanding frame. Now, initially at A, this is my sender's window. So it contains these 7 frames, 1, 2, 3, 4, 5, 6, 7. And it starts sending the data out. Now it first sent the frame 0, frame 1, frame 2. Just remember that I'm not talking about a stop and wait protocol here. So the sender does not need to wait after transmitting one frame. So initially it has sent 3 frames. This is my receiver's window. Once again, my receiver's window is equal to 7 here. So the receiver has got 7 buffers. Now, once the sender has sent F0, F1, F2, which corresponds to the 3 frames, the receiver accepts them, and it has to verify whether these 3 have been received without any errors or not. And once it is assured that there are no errors and everything is fine, then it sends an acknowledgement 3. If you observe, after sending an acknowledgement, this window or this edge of the window is now moved to here, which means that these 3 frames are now sent to the network layer at the receiver. So it is now expecting the next sequence numbers as 3, 4, 5, 6, 7, and 0 and 1. Come to the sender side. Initially, the sender has sent F0, F1, F2. So these 3 frames are sent but are yet to be acknowledged. So the window doesn't change much. It remains the same. Still, the sender has an option of sending 3, 4, 5, 6 because it has got 7 buffers. Once the acknowledgement 3 comes back, another important thing is when the receiver sends an acknowledgement 3, which we call as an cumulative acknowledgement, which tells you that the frames starting with 0, 1, and 2 have been received correctly. So unless until frames 0, 1, and 2 have been received, the receiver will not send the next acknowledgement, which is ACK3. So once this ACK3 is received by the sender, it understands that frame number 0, frame number 1, and frame number 2 have been received. So it has moved this edge from here to here, and this window is now slided further to increase or to add the next 3 frames because 3 frames have been acknowledgement. What about these? They are removed from the buffer because they are no longer required. These frames have been acknowledged by the receiver. So next what it did is it sent frame 3, frame 4, frame 5, and frame 6. So once these frames start arriving at the receiver one after the another, the receiver can either send an acknowledgement for each and every frame it receives, or it can send a cumulative acknowledgement. So in this example, once frame 3 is received, the receiver checks whether the 3 is within the receiver's window or not. And if it is happy, so it has simply slided further. So this window has been slided further. And for this 3, it has sent an acknowledgement saying ACK4. This ACK4 tells you that, or tells the sender that the receiver is expecting 4 next. So once this 4, 5, and 6 have been received, what it can do is it can shift this edge till here, and this can move slide further. So once the sender receives an acknowledgement of ACK4, and this will be done after 5 or 6, maybe in the future, if it says ACK7, automatically it means to the sender that all the frames till 7 or till 6 have been acknowledged, and this edge moves here. So once this edge moves further and further, the number of frames coming towards this part means that they are all successful transmissions. Here, what if you can ask me, sir, why did you say all this? Imagine if there is an F2 or F1, there is some problem with the transmission. What it can do is, as the frames are already in the buffer, and if it did not receive an acknowledgement for the timer that is set for each and every frame, it can simply retransmit from the sending window. Please remember that if this window moves towards this side and the frames are outside the window, these frames are already transmitted. They are already received without any errors. That is what the sender's window is. Now, another important thing here is the sender's window size need not be equal to the receiver's window size. Both of them need not be equal. Okay. Receiver's window size. Now, if hopefully you got the gist of what do you mean by a sender's window and what do you mean by receiver's window. To simply summarize in one point, the sender's window contains the frames that the sender wants to send or has been sent but not acknowledged. The receiver's window contains the sequence number of the frames that it is going to accept. Okay. Now, let me show you the first protocol under this category or under the bidirectional category, which we call as 1-bit sliding window protocol. The name tells you that 1-bit sliding window protocol should give you the idea that here both the sending window and receiver's window is 1, which tells you that the sender can only have one outstanding frame. One outstanding frame, that is only one buffer. And the receiver can only accept ordered data only. That means the frames have to be received by the receiver in order only. If there is no order for the frames, automatically the receiver has to discard them. I'll show you an example. Now the sender can send one frame and waits for the acknowledgement from the receiver. Only after the acknowledgement is received, the sender can transmit the next frame, as just like in stop and wait protocol. Let me show you a simple diagram which I have taken from the Tenenbaum's textbook, which it shows 4 different times. Okay, A, B, and C, and D. Now first let us talk about A here. What do you mean by A? What happens here? You can see that this particular edge, there are 2 edges here in this. Okay, there are 2 edges here, though both are the same position, like this. Now, initially at A, there are no frames outstanding at the sender. That means the sender has got no data to send. So the sender's window is completely empty. So both the lower and upper edges of the sender's window are equal. Both of them point at the or stay at the same location. Here, at the same time, because the size of the receiver's window is 1 and the receiver is only going to accept the frames in sequential order, it points to the fact that the receiver is going to accept only frame with the sequence number 0, because obviously sequence number 0 is the first frame in the list. Okay. Now, what about B? So in B, after some time, the sender's data link layer gets a packet from the network layer, creates a frame with the first sequence number and transmits it. So you can see here that in B, the data link layer has received a packet. And what does the data link layer do? It has to create a frame from that packet. So it adds a sequence number. What is the first sequence number can it add? The sequence number is 0. Now it creates a frame and then it transmits to the receiver. Now the sender's window size is 1 here. It can only have one outstanding frame. So it will send the frame number 0 and it will wait for the acknowledgement to be back. So unless until it receives an acknowledgement, the sender cannot proceed forward. Let me go to the C. So here this packet or this frame is yet to be received at your destination. So there is no change in the receiver's window. In C, let us assume that whichever frame, the frame number 0 sent by the sender has been received by the receiver, verified by the receiver, and there are no errors depicting a successful transmission. So what will it do? It will send an acknowledgement back to the sender and now rotate the window or slide the window to the next sequence number. So what does this tell you? It has to tell you that the receiver is now expecting sequence number 1 or the frame with the sequence number 1. By mistake, if this acknowledgement is lost and sender A has sent a frame 0, because once it transmits frame 0, there is a timer at the sender which will count down. If the timer hits 0 and there is no acknowledgement from the receiver, the sender will assume that this frame is lost during transmission, or there might have been some errors during transmission, and it will retransmit this particular frame. Let me go with the original scenario first. In D, as this acknowledgement has been sent to the sender, there is no problem, and assume that there is no data for the sender to send. So the two edges once again rest at the same place here. There are two edges here. And in the future, if the sender receives another frame, the data link layer adds the sequence number 1 and it will then send out, which the receiver has to accept. So in this way, we call this as a 1-bit sliding window protocol, where the sender has to send only one frame and has to wait for the acknowledgement to come back, and only then can he proceed to the next data transmission or the next frame transmission. There is a problem with this technique. It consumes a lot of bandwidth, and also the sender sits quiet for a very lengthy periods of time if your transmission distance is large. So in order to come out of this problem, we propose something called as pipelining concept, and the next two class of protocols which we are going to discuss in the next videos, which are go back and selective repeat protocols, both work on the concept of pipelining. So till then, take care, good luck, and if you have any issues, please feel free to ping in the comment section. Thank you.